Thank you very much. We resume our sessions. The next talk is from Tal Hassner from Open University, Israel. Tal, please.
Good afternoon, everyone. First of all, I'd like to thank the organizers for inviting me here. This is the title of my talk. It's a bit of a mouthful, I know, but it's actually a bit longer than that, because what I'm interested in is not just what action recognition benchmarks are telling us about action recognition performances. I want to try and figure out what they're not telling us about current action recognition performances. So, action recognition is an empirical study, and to show that your system works best and to have your paper accepted into a conference, you need to show that your performance is better than anyone else's on a standard benchmark. And I started out this sort of investigation by looking at what sort of benchmarks people have been using in the field in recent years. So this is a informal benchmark, action recognition benchmark popularity contest. So I went to Google and asked it to give me all the papers on action recognition in the 5 big conferences, CPPR, CCV, ECCV, ACCV, and EMBC, from 2010 to 2012. I found 36 papers. Now, the asterisk here is to mention that, I may have missed some papers that had clever names in their titles, behavior, understanding, and things like that. And it also is here to remind me that these are not necessarily, this only includes papers on action recognition from videos. So there's a whole field of action recognition from images. I didn't look at any of these. So 36, not necessarily inclusive of everything, but I think this gives a general idea. And I want to know which benchmarks people use and how many times was each one of these benchmarks used, and what does this say about action recognition. These are the names of the benchmarks that came up. Everything from the old KTH and Wiseman benchmarks in the middle of the previous decade to Wiseman, which was the newest one until the 101, UCF 101 that we're using here in this workshop. And this is a histogram of how many times each one of these benchmarks was used. So just right off the bat, you can see several things. First of all, others appears to have a very large number, and this is because many of the papers that came up are papers about very specific things like interactions, which require benchmarks of their own, and hand gesture recognition for sign language and stuff like that, which require benchmarks of their own. Another thing that pops out is that the oldest benchmarks are used the most, which is again not really surprising because these benchmarks are benchmarks that people have got used to using and feel comfortable with and have a lot of code designed for, I guess. How much, and the third thing is obvious when you look at the performances, state-of-the-art performances of these benchmarks. So these scores are true for about 3 or 4 months ago, I guess. I haven't checked for this, for ICCV, I haven't checked if these changed. I should point out that to be very, very careful, these numbers shouldn't really be compared from one benchmark to the next, because the definition of the testing protocol from one benchmark to the next is different. In particular, the definition of chance is different. For example, the Wiseman set is a binary testing protocol, so 50% will be chance. Anybody doing 50% is not really doing anything. And say the Wiseman set with 10 classes, I think it's 10 classes, that's 10% for chance. Okay, so looking at these numbers, something else is evident, and that is that 55% of the times that benchmarks we use, 55% of the benchmarks that we use in the last 2-3 years were these 4 old benchmarks. The 4 original, let's call them 4 original benchmarks, or 4 old benchmarks. And for these benchmarks, regardless of the definition of chance, the performance is almost 100%. It doesn't really matter what chance is, 100% is 100%. So the performance is saturated. Before I continue, right before coming here, I decided to see maybe something has changed in the last CPPR 2013. So what happened in 2013? 8 more papers were added to the bunch, 8 more papers that I found, at least, and this is what happened. So others seems to be a popular choice for many people. These are benchmarks that I can find like one reference for, so I didn't want to open up a new column. But it seems that the KTH and the UCF sports are really, really popular, and I don't know if any of you had a chance to go downstairs and look at the posters. UCF is still very, very much popular. UCF, yeah. Sometimes I confuse US, and that's completely different. So apparently nothing much has changed. Still 55% of the papers are using the 4 old benchmarks. So a legitimate question to ask at this point is what's wrong, or what problem is there with using these benchmarks? Why is this? Is this a problem? And if so, why is this a problem? So to answer that, I'll give several answers for that. The first answer for that is by playing a game called Name That Dataset, and I've adapted that from the work of Joraba and Efros, which they did something very similar for image benchmarks in CDPR 2011. So I'll give images some frames for frames for each one of the 4 old benchmarks, and let's see if you can recognize which one of the frames belongs to which benchmark. So you have these 4 frames. You have 3 frames, I'm sorry. These 3 frames, these 3 frames, and these 3 frames. Could you name the benchmark that, if you have any experience working with action recognition, I'm hoping that you can very easily tell that this is the Wiseman set. This is the ISMS set, the KTH set, and the UCF sports set. So following Joraba and Efros' conclusion, a warning, I should say, that if you can easily tell the difference between the benchmarks just by looking at them, that means that the benchmarks carry with them a very large bias. And that means that if you write a program to get high results, write an algorithm or develop an algorithm which gets high results on one of these benchmarks, it's not necessarily going to help you get high scores on the other benchmarks, in particular in the general problem of action recognition. So that's one thing that you can say about the old 4, they're very biased. Another thing that comes to mind when you're looking at them is the number of classes they contain. The Wiseman and KTH have 9 and 6 classes each. UCF Sports also have 9. IXMS comes up with a whopping 11 classes. It's a huge number of classes. This can be a problem or cannot be a problem, I don't know, but if you compare this to image sets, the picture looks completely different. You have hundreds of classes in the Sun database. You have 80 million images in the appropriately named 80 million tiny images data set. ImageNet, well, that's gigabytes and gigabytes of classes. I don't remember how many classes there has, but at least hundreds, if not thousands of classes. Even face recognition, the label faces in the wild, which is already considered old, has about 5,000 individuals in it, so 5,000 different classes. So it's a very, very different picture than the picture that we're seeing for the 4 old benchmarks that, again, 55% of the usages of benchmarks and computer vision papers and CDPR, ICCV, and so on are using. So there's a very, very big difference between what people are doing in images and what people are doing in action recognition videos. So looking back at the old 4 and at the high scores, it's reasonable to, if people are still using these benchmarks and using them a lot, it's reasonable to ask, what do these high scores tell us about action recognition? If they're being used a lot, maybe they do say something about action recognition, it's something important. So to answer that, I ran a case study, test. I took the Wiseman benchmark and I gave students the Wiseman benchmark as a homework assignment. I had 13 graduate students taking an introductory level computer vision course. I gave them a deadline of 4 weeks, and I told them that they can do anything that they like as long as they follow the protocol and implement stuff themselves. And My objective was to see how difficult was the Wiseman benchmark. I mean, people are still using it, so maybe it's really hard. And if I give this to entry-level computer vision students, I'll be able to see this. So, what were the results? This. So the first one or two students got an average precision of 40 and 50%. Needless to say, they didn't continue with a career in computer vision research. But the six top scoring students all got results which were better than high-profile publications as late as 2009. In particular, the highest scoring student got 100% average precision, a perfect score. So maybe he's, I don't know, phenomenal. Maybe he did something out of, or maybe he just took one of the very, very fancy new methods and implemented that to get this. So I looked at the method that he developed to see what it does, how it performs its magic, how it gets to 100, and to see how it works. So the method that the 100% average precision student implemented works as follows. He took the videos and started off by segmenting them to the foreground background. Now the benchmark comes with its own foreground background segmentations. I don't know if any of you here use this benchmark, but it's available, and I allow students to use this. But the thing was, this benchmark is so easy to work with. There's a static background, the camera is static, there's just one foreground motion, nothing was happening. So the student implemented a foreground background subtraction itself. So this is his work, okay? And then for each one of the videos, he computed seven scores, seven scalar values, seven numbers, features, whatever, which represented that video. What sort of numbers did he compute? Well, I'll just give examples of two. One was he looked at the center of the foreground mask, the center of mass of the foreground mask, and then he looked at how it varied and its Y position along the video. So remember, the camera is not moving, so any variation in the center of mass is just the variation of the movement itself, and then computed the variance of this movement. Okay, so for some reason, for some motions, I guess jumping up and down, there'll be a high variation. So standing up and waving your hands, there'll be a low variation. So that's one feature. Another feature that he used was he fixed a constant value, a constant column of pixels in the middle of all the frames, and then looked at the symmetry on both sides of the mask, how we just subtracted both sides of the mask across this. And that was another feature. And the other features were not more complicated than this. All very, very simple, very, I guess, basic stuff. Very intuitive. And he took these 7 features, and each video has a 7-feature vector of itself. So these are points in 7-dimensional space, and then when he got a new point, a new feature vector, he just looked at its nearest neighbor and used that for classification. And that was enough to tell him what action the new video was from. So the method was obviously accurate. You can't get much more accurate than 100% accuracy, right? It was accurate. It was really, really fast because he really didn't do anything. I mean, the nearest neighbor classification, when you have a benchmark that contains I guess it's 100, maybe 1,000, something like that. Because this is not a very complex search problem. But was it general? Can we apply this to other benchmarks? Could this be used elsewhere? So, to answer the question from before, what do these high scores say about action recognition in videos? Just by looking at the fact that he got a 100% average precision, I can't say very much about his capabilities or the method that he developed, the capabilities of the method that he developed as something for solving action recognition. I should note that this report will be published soon, so if anybody gets a paper to review and it has the Wiseman benchmark, so you'll have something that you can reference and say, they told me that the Wiseman benchmark is easy. We're now trying the same thing with the KTH benchmark, but this is an ongoing work, so I'll only know at the end of the semester how that went, and I'll be sure to tell you. So this brings me to the question. So obviously the four big ones are, well, I just tried this with the Wiseman, but I hope that that you agree with me that the other three old benchmarks will probably have similar problems, and besides that, they're very, very biased. We saw that earlier, and they're very small, especially in comparison to image sets. So what would make for a good benchmark? How would we design a good benchmark? A good benchmark would need to capture several things. It would need to be very, very, very large. And why would it need to be very large? Because it needs to reflect a lot of stuff that goes on in, in action recognition, in videos. A lot of stuff that we expect to find when we get videos as input for action recognition systems. It needs to be able to capture the very, very large variability of how things look. The same action can be performed from many different angles, many different viewpoints, many different places, many different contexts. One of the major problems that we had when we assembled our own benchmark, and I'll mention our own benchmark in a minute, is the issue of class resolution. And in fact, the MAR winner paper, I think, for ICCV was about the similar subject of class resolution in the context of images, of image classification. I mean, I'm showing these two videos here, maybe I'll show them again. These two videos here, are these two videos of people swimming? Or are these two videos of two people, one of them backstroking and the other one, I'm not sure what that particular stroke is called, but a different stroke. So at what level do we define the class labels? This is a problem in images, as I mentioned earlier. I think this is a problem which is much more acute when you're talking about videos. Actions can be very ambiguous. If you get any one of these videos and you're asking what is sane and what is not sane, for example. So again, just to show you, the video on the left, you have two guys walking and high-fiving each other. The video in the middle, you have just two guys high-fiving each other. And the video on the right, you see a guy walking. So are these videos people walking, high-fiving, what's similar and what's not similar? People can do many actions at the same time. How do you define these composite actions? And a benchmark for action recognition needs to take care of all of this. It needs to reflect all these composite variations that you have in the videos and the queries that you're working. And finally, there's a lot of stuff that is very difficult to define. Like in this case, how would you label something like this except, I don't know, called social security? Not social security, social services, I'm sorry. Called social services. How do you define stuff like that? But that's an action, and we understand it when we look at it. Sorry?
It's an inverse pendulum problem.
Inverse pendulum problem would be my label too. Ivan gave a very nice talk which sort of broadened my own horizons. So she gave several examples of other stuff that you need to take care of when designing a benchmark. One of them is intent. This guy over here and this guy over here are doing the same thing or not? I think you showed that with pictures. I tried looking for something like that and spent a whole day looking for videos of doing something like that. So, is this the same action or not? Both of them have hoses. Low-level semantics, maybe they are. High-level semantics, maybe they're not. But intent certainly plays a very important role when you're looking at these videos. They're still watering plants, isn't it? It's one video. Context is also very important. In the following video, you just see two hands. You don't see any action. But despite that, you know exactly what's going on. You don't see legs moving, you don't see hands moving. There is context. This context can either be temporal context, stuff that you saw a few frames before or a few frames after, or just context in terms of your general knowledge about how humans behave. When you're seeing a video with two heads rotating one around the other, you know that this has to be dancing. But if you're just looking at the low-level information, there isn't any dancing in the video. So again, if you're designing a benchmark to faithfully capture the problem of object action recognition, you need to take all these things into account, which means that the benchmark you need to develop needs to be very, very large. Two recent attempts to develop benchmarks to answer some of these problems. One of them is focuses on similarity labeling rather than action labeling, or multi-class labeling. And this is our own work of the Hassner benchmark, where we're looking at binary action similarity rather than labeling. So you're given two videos, and your objective is to answer, are these two videos, in these two videos, are the actors doing the same thing or not? And we were hoping that this would make the problem of collecting the data and measuring performance and designing methods to deal with this problem easier. But as several people have pointed out, this still leaves a lot of ambiguities. What is the same action? So this again brings us to questions of intent, questions of context, questions of hierarchy, action hierarchies, semantic hierarchies, swimming versus backstroke versus so on. So just to give an example, is this the same thing as this? In both cases, they're squatting, right? Probably for the same reason. In both cases, you're working your muscles to get them buffed, I guess. But you wouldn't naturally label this the same. And some people actually did label them the same. So this doesn't take the problem away. This doesn't make the problem go away. Another attempt at taking action recognition benchmarks to the next level is, of course, the action recognition that we're using here, the UCF 101 classes. So this is a really nice attempt because, first of all, it dramatically lifts the number of videos that we have at our disposal to learn from. 1,300 videos is significantly more than any previous benchmark. And 101 classes is, Aslan may have more, but it's not defined as an action class, and there's a lot of sort of mismatches in the classes themselves. So this is the first time that 101 classes are offered in a very clean way. These are the classes over here, and this is very good, as I said, but is 100 classes really enough? To sort of back me up here, Caltech 101 was one of the major benchmarks that people were using for a long time, and people were saying, well, image classification is saturated because everybody gets really high results on Caltech 101, but we all know what happened next. There's something like the ImageNet, which sort of opened up stuff and performances dropped because the real hard problems occurred when you have an order of magnitude more classes to work with than 101 classes. So this is an excellent step in the right direction, but we still need a lot more videos to capture all the stuff that I mentioned earlier. So I'll pretty much wrap this up by talking about some of the lessons learned at least as far as I'm concerned, by looking at the things, at the benchmarks that people were using. The four old benchmarks, the older benchmarks are very much biased, which means that if you develop something for one of them, it will probably not work for others, or there's reason to believe that it will not work for others. They're very easy to work with. I mean, graduate students with no prior experience can get really high results on them. That says something. And probably should be avoided if one of you gets a paper to review with take heed. So that's the older benchmarks. Newer, more recent trends is more videos, a lot more videos, which is very, very good. More classes, a lot more classes, which again is very, very good. Just to give you an idea, things like WikiHow, for example, which have a lot of different videos for a lot of different ways of doing it, they already have thousands of action classes there. And there's probably other, YouTube has, if you mine YouTube for labels of how to do things, there's also thousands of different classes there. So the data is there, we need to collect it and assemble it somehow, but it's there. And more evaluation protocols. Again, similarly to what people have been doing in image processing, in image-related problems. Before I go, I'll just say I happened to talk to someone earlier and I mentioned action recognition. That person says, well, that problem is saturated, isn't it? I mean, it's pretty much solved. So I think one of the lessons that I'm doing, the most important lesson that I learned from all of this is, no, it's not solved, but the benchmarks that people are using make it appear so, and this is, I think, a very dangerous place to be at as a field, as a problem, and we need, I think, to shake that off and try to make benchmarks a lot more challenging. I think this workshop is an excellent place to do that. So, yeah, thank you very much.
Thank you, Tara, for recording interventions. Are there any questions? I'm starting to get a bit late here on, please.
So I've heard a complaint in the field that actually you can't get a page through the review unless you include KTH and Wiseman results. So should you address the reviewers in a different way?
It's really funny that you're saying that, because I had a paper very recently, one of the reviewers wrote that. Why don't you have a result on the KTH benchmark? We didn't send one because I know there's some people here who are familiar with the KTH benchmark, but we thought that 96%, 1% here and there, and KTH and other benchmarks, by the way, have other problems that I didn't mention, like the problem that the protocol is not well defined, so it's difficult to compare results. There's a lot of issues associated with KTH. What we did at the time was we said, look, we have results on 3 big new benchmarks, and if you want, we can add KTH as well. And we were lucky enough that we had results in the KTH, but we didn't include that in the paper itself. I'm afraid I can't give you sort of a general password that would make reviewers sort of automatically say, well, forget, because I know this is a problem with the KTH. I know this is a problem with some of the reviews. This is what I'm trying to change in this particular talk here. I've felt this problem myself when I submit papers. As a reviewer, I promise you, I don't ask for KTH.
So we can include your citation from now.
And it's not, the paper hasn't been published yet, but very soon it will, especially if we get good results on KTH with students.
I think I have a quick comment about this, that basically the pattern has been there for many years, that you wouldn't want to have one old benchmark and one of the new ones.
It's like a sanity check, I think.
Yeah, to reassure people that you will still perform and kind of saturated accuracy. It's more like, no, to be sure that the technique for some reason doesn't fail easy cases, not as the real point that you want to prove. And that's a 55%, because on average, I think every paper has at least 2 benchmarks, one of the old, one of the new. So
I think the standard number would be 3. The 3 is the magic number that you make.
Obviously, on the instance. But
old benchmarks already are, UCF Sport is already an old benchmark. You don't have to go so far back as to, yep.
So what is the best result of Hassner?
Hassner is still very far from being saturated. As far as I know, the best result is 68 or 70% accuracy. I don't remember the AUC.
And that's yours?
That is ours. We were so far we're one of the most active people working on Hassner. But I hope this changes. But
so what's the reason from your point of view? People are not able to beat that.
The reason that it is a difficult benchmark to beat is because the way the benchmark is set up makes it very, very difficult. This is actually a complaint that I'm voicing towards myself. This is one of the bad aspects of a criticism towards my own benchmark, and that is that even to do something simple like such as same not same, you would need a lot more videos to learn from, a lot more data. The 2 images that I've shown of the squat and the man lift, those would classified as the same. So imagine how many videos you need before something like that would be easy to spot as the same. So I think the major reason for Hassner still being difficult is the fact that despite its size, it's still far from being big enough.
So another reason something like UCF Sports shows up again and again, because there aren't that many action localization data sets, and it's one of the ones that has that. And I think that it's probably indication maybe we need more, but I think that part is even more, it's more expensive and hard to get labeled.
I think UCF Sports has a sort of a dip in performance. If you remember the graph that I showed earlier, and I think one of the reasons the dip is there is because you have the localization bit that you need to add. It's a challenging problem on its own. Maybe I'm throwing it out there. I have absolutely no idea. Maybe you need to formulate action localization as a problem unto itself. Maybe you need to stick that, wrap that along with action recognition. So I don't know what the correct answer is, but it certainly makes the problem harder having to localize actions. Yeah. But still, the performance is pretty high, even on UCF Sports. So that says something about the method.
So you mentioned that there is we have few classes for actions, but also classes that are difficult to define. Like you argue that we should both.
Yes.
Contradictory.
Just
the result is.
This is true. This is something that's I wouldn't say keeping me up at night, but it is keeping me up at night. This is one of the major problems in the field is how to define the classes. I've seen several different ways of doing it. One was ours, just avoid the problem and look at saying, not saying, and that's it. So behind the scenes, we have class definitions, but we didn't really use them. What we used are people that sat down and labeled the same, not saying, saying, not saying. And if the labels mismatch, then they mismatch. So that's one way of doing it. Another way of doing it is maybe going about the way that ImageNet did. I'm not sure if I know of a good repository. I didn't look, but a good repository of verbs maybe, or actions and definitions, and you can sort of pile up a lot of videos for each one of them and ignore the problem that there's a lot of intra-class similarities. I'm not sure how to resolve this problem. So this is a serious issue. What you mentioned right now is a serious and real issue. You need to break this sort of glass ceiling by adding more classes, but it's really difficult to define more classes. I don't think people are lazy, and that's the reason why there's no bigger data sets. I think it's really, really difficult to make the data sets bigger.
Okay, so just one more question.